Hey everyone, welcome to another episode in Physics is Fun. Today is going to be about more momentum with a collision. Let's jump into reading the question. A small block of mass m sub 1 equals 0.50 kilograms is released from rest at the top of a frictionless, curved shaped wedge of m sub 2 equaling 3 kilograms, which also is on a frictionless flat surface. When the block leaves the wedge, its velocity final, v sub f, equals 4 meters per second. A. What is the velocity of the wedge after the block leaves its surface? B. What is the height of the wedge? Let's move on to drawing the picture. The picture has a curved wedge, something like this, which is the mass m sub 2. At the top, there is mass m sub 1, and the height of the wedge is h. Mass m sub 1 slides down the wedge like this, and this creates movement like this. With the wedge m sub 2 here, and m sub 1 moving at the bottom here at the final velocity. M sub 2 also slides back, moving at velocity v sub 2 like this. Both pictures show the start to finish movement. There is quite a lot to deal with, so let's write down some variables. The mass m sub 1 equals 0.5 kilograms, m sub 2 equals 3 kilograms, height initial equals h, and height final equals 0. The velocity sub 1 initial equals 0, and the velocity sub 2 initial also equals 0. The velocity sub 1 final equals 4 meters per second, and the velocity sub 2 final equals unknown. That's what we are trying to solve for part A. Let's think about what equations we need or can use with all our variables. Looking at the problem, it doesn't seem to be a collision, or definitely not elastic. But taking a deeper look, this is a backwards inelastic problem, where the masses start together with the same velocity and end up with separated masses at different velocities, opposed to maybe what we're used to, where the masses are separate first, then collide together. I will circle back after looking at the equations. With mass and velocity, the relationship exists in momentum, and adding height to that exists within conservation of energy. Remembering the equations, momentum initial equals momentum final. And for energy, the lovely equation, kinetic initial plus potential initial plus the work of non-conservative forces equals kinetic final plus potential final. Expanding out momentum is m sub 1 times v sub 1 plus m sub 2 times v sub 2 equals m sub 1 plus m sub 2 all times velocity final, which they do both share. Thinking deeper about this, both objects start together and at the same velocity, which seems to satisfy that right side of momentum. And then they collide and end up split with individual velocities. So both of the initial velocities in this case are actually the final velocity for our momentum equation, and have to remember we are working backwards, which I spelled wrong. Nice. With all the equations and variables set up, let's move on to part A, where it is now time to calculate. Rewrite the momentum equation, P initial equals P final, and expanding gives m sub 1 times v sub 1 plus m sub 2 times v sub 2 equals m sub 1 plus m sub 2, all times velocity final. Remembering our velocity is actually 0, so that right side all goes to 0 and can be crossed out. This leaves just m sub 1 times v sub 1 plus m sub 2 times v sub 2 equals 0. Now we need to solve for the velocity v sub 2, so subtract both sides by m sub 1 times v sub 1 and cancel on the left to get m sub 2 times v sub 2 equals negative m sub 1 times v sub 1. Now divide both sides by m sub 2 and cancel on the left side to get v sub 2 equals negative m sub 1 times v sub 1 divided by m sub 2. Plug in numbers now to get negative 0.5 kilograms times 4 meters per second, all divided by 3 kilograms, which comes out to negative 2/3 meter per second. So the velocity for mass m sub 2 equals negative 2/3 meters per second, going in the opposite direction as mass m sub 1. With part A solved for, let's move on to part B. We have what we need to solve for h now, and remember to now not work backwards like we did with momentum, and work forwards with our energy equation. So let's calculate. Rewrite the conservation of energy, K initial plus U initial plus work sub and C equals K final plus U final. Again, there is no work done here, so that can be crossed out, which I forgot to do. And now expanding, we would get a long equation usually, but for this problem, we are actually now working with two different masses, which both have kinetic energies, so we actually get an even longer equation of 1/2 m sub 1 times v sub 1 initial squared plus 1/2 m sub 2 times v sub 2 initial squared plus m sub 1 times g times h initial equals 1/2 m sub 1 times v final squared plus 1/2 m sub 2 times v sub 2 final squared plus m sub 1 times g times h final. Thinking about all the terms that are 0, the initial velocity for both masses are 0, since they start from rest, so can cross those out, and the height final is the ground, so equals 0, so cross that out as well. This leaves a nicer equation of m sub 1 times g times h initial equals 1/2 m sub 1 times v sub 1 final squared plus 1/2 m sub 2 v sub 2 final squared. Now we have two unknowns, but we previously had solved for v sub 2 and can substitute that in to get 1/2 m sub 1 times v sub 1 final squared plus 1/2 m sub 2 times negative m sub 1 times v sub 1 initial over m sub 2 all squared. Remember that this initial velocity is actually the final since we had it worked backwards before, so I replace it with v final from now. Multiply out to get m sub 1 times g times h initial equals 1/2 m sub 1 times v sub 1 final squared plus 1/2 m sub 2 times m sub 1 squared times v sub 1 final squared over m sub 2 squared. We can cancel out one of the m sub 2's over here. On the right side, both terms have m sub 1 and v sub 1 final squared, so we can factor those out from both. And this leaves m sub 1 times g times h initial equals 1/2 m sub 1 times v sub 1 final squared, all times 1 plus m sub 1 over m sub 2. Now to finally solve for h, divide both sides by m sub 1 times g, and cancel both on the left side, and cancel m sub 1 on the right side. We are left with h equals v sub 1 final squared over 2 times g, all times 1 plus m sub 1 over m sub 2. Plug in numbers to get the 4 meters per second squared over 2 times 9.8 meters per second squared, all times 1 plus 0.5 kilograms divided by 3 kilograms. Calculating out gives the final height of the wedge to be 0.952 meters tall. And with that, we have solved part B. After dissecting this problem and realizing this is a backwards momentum problem, found that the wedge moves at negative 2/3 meters per second, and using this velocity, find through conservation of energy that the height of the wedge is 0.952 meters tall. I hope these intro problems are as helpful for you as they are for me. Thanks so much for watching. Hope you come back to learn more exciting material, and see you next time.